According to the Oxford Dictionary, the definition for practical is connected with real situations rather than ideas or theories, which is the main ethos of this presentation. So, why am I here today to talk about how to develop and manage your site's power system model? Because in a nutshell, the development of a power system model can be complex, and if managed incorrectly, the power system model will not serve you in making sound decisions about your site's electrical distribution network. So I believe a practical approach to managing your site's power system model is essential. Systems, such as those found in electrical grids, industrial plants, mines, or pretty well any infrastructure within an electrical distribution network. And I guess in Australia, well, there's many different power system model software packages that you can use to do this. For networks containing multiple buses, such as a mine, the two most commonly used in Australia, or New South Wales in particular, SKM Power Tools for Windows or ETAP. There's more, but these two would definitely be the most commonly used. And typically, once an operation has invested the time in building a power system model in one software package, the operation would usually stay with that one software package and not shift. Although we have been involved for one reason or other to swap one over, it is a large task. ETAP and PTW models are not compatible with each other, so to change over you actually need to build the whole model in the new software package. So an expensive task. Another way to look at this is, I guess once your network reaches a certain size, it's no longer viable to just use AS3000 or other rules of thumb to make design decisions about your network. And also, it's a requirement of the mining regulations to consider the rating and design of plant for the prospective electrical fault level, electrical load, operating frequency, operating voltages, arc fault control when preparing your electrical engineering control plan, which this all can be accurately done via a series of studies with a valid power system model. So, how does this relate to safety? Well, properly managing your site's power system model is essential to minimise the safety risk to people near faulted equipment, ensuring your electrical distribution network is operating within the equipment's design constraints, avoid damage to unfaulted equipment, and to minimise the damage at the point of the fault, to understand and manage arc flash prospective incident energy levels at locations throughout the distribution network, and of course, maximising reliability. So, how should you approach developing and managing your model? How do you ensure successful power study outcomes? And most importantly, how can you achieve this efficiently and effectively without breaking the bank? Let's summarise it down into 3 stages, which are step 1, data entry, step 2, run studies, step 3, document and manage the results. So step 1, data entry. How do we better collect and manage up-to-date field information for entry into the model? So the model is only as good as the information put in it. Hence, a clear strategy for collecting and managing accurate and up-to-date field information is essential for a model to closely represent how things actually are in the real world. If you put quality information in, you'll get quality information out. If the model contains outdated, half-complete information relying on assumptions, there will always be questions about the accuracy of studies completed based on that model. Therefore, there is great importance for clear strategies for field data collection. Some practical tips to efficiently manage field information. So when it comes to new electrical infrastructure, anything that's brand new or greenfield, it's important to ensure drawings are provided by your designer or the design team, and that those drawings are accurate. Drawings need to contain the required field information for entry into the model. So this can be managed well by setting a standard for your drawings for your site, in your site electrical documentation standards, and ensuring your designer understands this requirement up front. It's also important to verify the drawings upon commissioning and develop as-builts. In addition to this, getting your electrical designer to build a model is good practice for the project, which can be included in the site master model once the project's been commissioned. Existing electrical infrastructure. So existing electrical infrastructure, if you haven't got the information in there already, collecting this field information, it can be an onerous and ongoing task. So in many cases, site electrical drawings no longer reflect what is in the field. Therefore, a physical audit of field electrical equipment will more than likely be required. In most cases, isolation will be required to retrieve the required information. And if you have the luxury of being able to turn things off to inspect, this can be done simply by coordinating between your consultant and your trades team what information needs to be retrieved from the field. But more often than not, turning things off can be difficult. Another strategy can be you can use existing touch points with the field equipment to gather the data. So one way to do this is to include the retrieval of field information in scheduled routine maintenance. In scheduled routine maintenance windows, information can be routinely gathered. Putting the information that needs to be gathered on work orders. Depending on your inspection frequency, the information asked for on work orders can be spread across multiple maintenance windows. If your site allows, photos of equipment really do provide a better insight for the power system modeller rather than just writing the information down. Often information is written down wrong. So photos, if you can do it, I know underground it's an issue, but for anywhere that you can even get a permit to get photos, it's very helpful. And it's really important that once information is gathered, to consider storing and organising this information in an organised manner. There's nothing worse than 10 photos of the inside of a switchboard and not understanding what switchboard that belongs to or what part of the switchboard, etc. So, really make sure you up your game with organising that information and get off to your consultant. And the third sort of strategy is change management. So for sites where the power system model has been accurately modelled already, it's important to consider change management. So when equipment is replaced or upgraded or sections of the network are configured differently, the changes should also be updated in the power system model. If this is not managed closely, it does not take very long for your power system model to become outdated. And then once it's outdated, it will require a large audit to verify its accuracy. A practical approach to this is to have an internal process for tradespersons that when changing a component out, to record the old information and the new information on a change management form or equivalent. Keeping on top of this, record keeping as you go can save a lot of time and effort and money down the track in keeping your power system model up to date. Step 2, run studies. So correctly calculate system parameters based on realistic study scenarios. The 4 baseline studies that should be done for all operations at a minimum, include short circuit studies, load flow studies, protection and arc flash, which depending on the nature of your operation can be extended to include further studies such as harmonics and power quality. And really the amount of power system studies that can be done, there's a lot out there, depending on the complexity of your system. So short circuit studies. So short circuit studies are the calculation of prospective fault levels. So we recommend this to be done to IEC 60909 standard, which is an international standard method for calculating short circuit current calculations. Once fault levels have been calculated for all buses within your network, it's important that this information is reviewed against design fault levels of your equipment. One important thing to consider is that it's important to review your short circuit study upon any changes to incoming utility or arrangement fault levels or power station fault levels. Fault levels do typically rise or go down over time based on changes in the network, and these do make a profound impact on your power system model, particularly the short circuit study. Load flow studies. So load flow study is essentially a more sophisticated review of your site's infrastructure's maximum demand. Load flow studies are essential for future planning and understanding how much capacity you have left in your network. Also to understand where the power is flowing and to prevent overloads in cables or equipment before it happens or before the protection trips. Load flow studies are only as good as the information you put in, as per everything in power system modelling. So for greenfield projects and something that hasn't been built yet, your load flow will have to be relied on typically based on calculated loads with consideration for diversity factors, whereas if it's been built and it's been commissioned, load flow studies should be based on measured data. It's nothing better than actual measured data, not calculated. So either by using a power logger, installing power meters at appropriate locations throughout your network, and communicating that information back, if you have the luxury, via DCS or SCADA system. So I think this is probably something that's important to consider, like the cost of putting a power meter in to a switchboard at certain locations throughout your network up front will save you down the track on doing power logging if you don't have that infrastructure in place. Protection studies. So protection studies is the coordinated study of a protection tripping curves that to ensure during a fault your network's protection system disconnects the smallest amount of the part of the network necessary to clear the fault, operates as intended, coordinates with upstream protection devices, minimises damage at the point of the fault, and minimises safety risk to people near faulted equipment. So during this study, the protection engineer must review protection systems for all operating conditions of your network to ensure that the device will trip during all scenarios that equipment can be operated in a faulted state. At a minimum, the output of a protection study should have a series of time current curves showing the protection curve of each device, including the damage curve of the equipment being protected. So I've been asked by the regulator to include in this the damage curve of the equipment being protected. That sometimes apparently is left off. It's also important that the protection study has a table with protection settings for each device, including specification of protection functions to be enabled in relays and circuit breakers. Once settings have been determined in a protection study, it's important that the settings of the devices in the field reflect the protection study and are not changed from that stated in the protection study without consultation with your protection consultant. Otherwise, really, you risk the protection system not operating as intended during a fault. Arc flash studies. So we're in 2023, hopefully everyone here has a very good understanding of what arc flash is and the risk involved. So we have to do arc flash studies. So an arc flash study is essentially an extension of a protection study. In the case of an arc flash study, incident energy of an arcing fault is considered for all locations within the study. Arc flash studies are rarely conclusive after the first round of calculations, as the incident energy levels of industrial electrical systems are often higher than acceptable risk levels. Therefore, it should be considered that when managing arc flash on site, typically will require a sequence of studies to be complete. Firstly, understanding the incident energy levels at all locations prior to introducing any engineering controls, then working towards mitigating incident energy via strategies such as improving protection coordination, introduction of arc sensing relays, and fault limitation with fault limiting fuses or similar. So up here is an example of what that process would be. So I guess in the first step, you do your initial baseline arc flash study. That'll tell you what your incident energy levels are at all locations. Usually once the first one's done, you'll find out where all your problem locations are depending on the maturity of your organisation. Once you figure out the places that you have found an incident energy level that's higher than what you are willing to accept, it's important to go then and have another go and do some more studies to try and figure out some solutions on what you can do to reduce your incident energy levels. There is a lot that can be done with engineering controls. It's not infinite. Some instances you do need to redesign some parts of your system. But stage 2 would be going through and doing those studies and figuring out a strategy. Stage 3 would be doing detailed design of that strategy, and stage 4 would be doing your supply and installation of that strategy, and of course, once you've got your as-built, updating your master model. So when getting your chosen consultant to run studies for you, it's important that everyone is on the same page. Before studies are run, it's important to understand and communicate to the consultant the intended outcome of the study. It's important to ensure the model is complete with all the required input information. It's important to ensure that studies are run based on realistic study scenarios that replicate real life. If possible, you will find efficiencies if you can run studies together, and to ensure that studies will reference all required applicable standards. And it's important to define the correct study parameters for your site, such as the incident energy levels, like the control levels that you have on your site. Often they are different than NFP 70E. This information, a really practical way to do all of this is this information can be addressed clearly in a well-defined design brief provided to your consultant, or by specifying these requirements in an overarching site power system modelling specification or standard. There really is little to gain by running studies without the correct information. If proceeding with assumptions, it is important to understand the impact of those assumptions and what sections of the results are impacted. Righto. Step 3, document and manage the results. So once studies have been run, the results need to be documented and managed. So once the studies are complete, the results need to be communicated back to the site's engineering team via a detailed report. The report should clearly outline the methodology used, define the method of sourcing the input data, outline and justify all assumptions made, and provide the results of the study with recommendations. Upon reading the report, make sure the significance of the study's results are well understood. To ensure a good handover between consultant and engineer or site representative occurs, it is best practice to ensure that you set up a meeting to discuss the outcomes of the report. When doing this handover, it's important to understand if the report studies are conclusive and have been completed. So that is, that minimal to no assumptions have been made, and all assumptions that remain are justified. What recommendations are there? Are there any action items that require further studies to be carried out? Has the report covered the study intent? Once studies are conclusive and complete, some questions to consider. How do you manage your site's master power system model? It's important to ensure a clear process is followed for revision control of your site's master power system model. Whenever there is a physical change on site, once commissioned, the master power system model needs to be updated. If a project has been recently commissioned, does your power system model need to be updated? So future project work should not be modelled in the site master power system model until it has been commissioned. The site master power system model should reflect the as-built status of your site. So during the design phase of a project, a copy of the master should be booked out and isolated from your master power system model, with all project changes modelled and the studies for the project complete. And upon commissioning of the project in the field, the master should then be updated as soon as practical to ensure that the master remains current. Do you document these standards in an overarching report? So it's best practice to do this. Have an overarching report for your site. That way you can just clearly grab it off the shelf and figure out what's going on. And do individual projects require their own set of studies? And yes, it is best practice to do so, yes. So in summary, again, step 1, data entry, ensuring that you efficiently collect and manage accurate, up-to-date field information for entry into the model. Step 2, run studies. Ensure your studies correctly calculate system parameters based on realistic study scenarios. Step 3, document and manage the results. Implement the findings to ensure that the studies are conclusive and do not require further work. And that's it. So before I finish, what does the future of power system modelling look like? As our power systems become more complex with inverter-based technology and with more cogeneration being installed throughout sites all around New South Wales, with this shift, the need to understand what is going on with your electrical distribution network is more important than ever. So in extension to the 4 main studies mentioned in the body of this presentation, emphasis is shifting towards further understanding of your network's impact on the grid as a whole via presentation 2 back from this one sort of touched on that with the Broken Hill network. Operations currently offsetting their usage or exporting with various methods of cogeneration. The larger that it is, they'll need to understand and demonstrate that the generators impact the grid stability. So in summary, power system modelling is an investment in safety, compliance and system reliability. If approached with pragmatism, you can get a whole lot of value out of completing your site's power system studies using this approach. I truly do hope you've found value in this philosophy that we put together. And, you know, it's beer o'clock, so hopefully not too many questions.